All right, good morning, everybody. Good to see you all. Let's review a little bit from I guess it was last week. Yeah, that is really interesting. So today we're going to move into talking about, so she says it's interesting there's planetary systems we're discovering that don't have stars associated with them. This is completely brand new from this year, or I guess technically last year, but within the last calendar year. So it was rather surprising a few decades ago that we saw planets at all that didn't have stars, but that's been known for a little while, that they would be co-orbiting one another as if they were a solar system without a star is completely bizarre. And today I'm going to try to wrap up the discussion of planetary formation. We talked a little bit about the birth of stars last week in general in your quizzes and textbook was going through planet formation and star formation. And this piece of the puzzle hasn't even made it into the discussion yet, as far as I can tell. I'm pretty sure that hasn't made it into the textbooks yet. But it's certainly going to inform where our ideas are headed in the future because things are changing very quickly. So yeah, what does it mean? I mean, interestingly, those planets that are seen co-orbiting each other, they're very big Jupiter-sized planets, right? Brown dwarfish, on the border of brown dwarf, Jupiter's mass planets. So, I guess this will make sense to come back and revisit as we talk about this idea of how planetary systems are assembled, if there's a role for metamorphosis and them changing forms across time, if you can grab planets from other systems, these kind of more discrete, almost catastrophic changes that happen to solar systems are very cutting-edge ideas. So that is really cool stuff. We'll get in. It'll make more sense soon. Yeah, or out of balance. Yeah, so she brings up the sort of most generous interpretation of the Greek pantheonic structure with all these different gods, and I think this is probably correct, that the Greeks were actually identifying the different emotional systems inside of the mind that sort of sum up, in the best case scenario, to the sense of self, to the self that's able to organize all of these different subroutines and so forth, which is honestly a very modern psychoanalytic way of looking, in so much as psychoanalysis is not dead. It's a very well-reasoned way of approaching the psyche. And then she also brings up this character, Julian Jaynes, who was a philosopher and writer who had this idea that the primitive people is actually not even that primitive, all the way back to the Bronze Age, were in some sense responding to these voices in their heads as if when we say we have thoughts, you hear this voice, and obviously today, most mentally healthy people would say, well, I'm just kind of talking to myself, or I'm hearing my thoughts appear. But Jaynes says, no, people prior to the behaviorally modern human, which was very recent in his estimation, that people heard those voices and thought they were actually deities telling them what to do, essentially. They didn't recognize it as a part of their own self that was integrating all of the whole of their subroutines and so forth. So, and I think there's some interesting merit to that. I'm not sure about his timeline with respect to how quickly that happened, but he seems to be onto something, especially with regard to how the left brain and the right brain interact, especially in the modern world where it seems like the left brain is extremely dominant in our civilization today. This is the analytic, logical one that expects order out of everything. And so Jaynes' idea is that the left brain, having hijacked the whole brain or taken control of the ship, is a very modern event, but who knows, really. And so he analyzes all of this literature all the way back to Homer and parts of the Bible and all of this and tries to make the case that people didn't have this first-person perspective that we all identify with today, and makes some historic analytic case for that being the case. So who knows? That's a good point, though. So you make the case that stars require other stars to go into them, especially star systems like ours, which are most evident on the planets themselves. So, for instance, and this is going to make more sense as we talk about a little more detail today about how stars form and and actually how they die, too. The big elements, right? The big atoms, let's say a lot of these metals, so I can't really get at this periodic table, but everything essentially after iron is very difficult to even make in a star, period. Now, in a star like ours, the biggest thing you're going to make is helium, which is the second character on this periodic table, so the second smallest, let's say. Maybe as the star dies, you're going to start making some carbon and oxygen. We'll talk about how that happens today, a star like ours. But, our star is pretty run-of-the-mill. Most of the stars are not making those heavy elements. And yet, look around the room, we have a lot of heavy elements. We have iron, we have big metals. And so where the heck do they come from? And the best theory, well, not the best theory, but the one that we've leaned on to this point is that the violent explosion of stars actually produces a lot of these heavy elements. Now, I should say that, and I brought up this example before, but there's some really interesting potential counterexamples to this theory, particularly this star, which you can read about, called Shibilsky's star, for which there have been observations of these very heavy elements that have half-lives on the order of a day, maybe 15 minutes, some of them, that are being found in the atmosphere of this star. And so the question becomes, how in the world does an element that only lives for 15 minutes appear in the atmosphere of a star? It's a pretty big star, but it's not outrageous. It's comparable in size to our sun, maybe a little bigger. How in the world does that thing have elements that have only been around for 15 minutes living in its chromosphere, or in its atmosphere, in its corona, right? Well, one possibility is that the stars are actually capable of fusing big elements, but they do it in a way that's outside of the theoretical structure that we're presenting in this class, which is where everything's happening inside the core. Maybe there's something like that lattice-confined fusion process that we talked about, which people are messing with in NASA to try to do this room temperature ambient fusion, which would be a lot more power efficient and desirable, right? I mean, fusion's a really desirable power source if we can develop it, but right now it's very, very energy intensive, expensive, really hot, unstable reactions. So if you can do it at ambient temperatures, if you can do it at room temperature, that would be a huge boon. So Shibilsky's star is really something to consider. And it's funny because you can go read about it on Wikipedia right now, and I recommend everybody does. The explanations for why it has these short-lived, huge, large atoms on it are kind of, well, they're strange to say the least. Almost nobody's considering that there might be other fusion processes going on. I think one of the top explanations is that aliens are dumping their trash into the sun, which is completely possible, I suppose. But there might be something else going on there that's a bit more mundane, as far as I can tell. So yeah, we got a lot of heavy stuff around here that must have come from somewhere other than our sun. Somebody else made it somewhere, as far as we know, unless there's something going on in the sun that we don't know about, which there might be. But we don't see those same traces in our own sun. We don't see those short-lived heavy elements. Cool. What else can we recall? She raises the question of how religions become less popular, although it's strange because it seems to be sort of good for the people that adopt it at the same time. And the case is made, at least I raised the question of whether we can actually live without it. So as much as we try to eradicate it from ourselves because we think of ourselves as increasingly rational people unable to stomach the superstition, can we actually get away from having a unified mythological value structure? I don't know. Does anybody have any thoughts about that? Is it something that we should do away with? I know this is kind of a scary thing to stand up and talk about. I'm just curious what you guys think, honestly. Yeah, please.
I think like most of society, religion has become more individualized, so it's not the fact that it's been kind of drifted away, it's just the fact that people are coming up with their own ways to kind of...
That's right. I think that, and that's what Nietzsche said, right? That in the 20th century, people would have to invent their own, right? The question is whether whether that's, let's say, commensurate with a peaceable way of life. Like, can people have opposing value structures and still coexist together? Or do we need to have a shared value structure in order to work together as a people?
Another thing is that socially we've begun to adopt a value structure that isn't necessarily related to religion, but is still very similar to each other in regards of social justice or stuff like that. So in a way, that's kind of replaced it.
100%, yeah, I see that for sure. Yeah, and the question is, what is the proper modality to like celebrate? You find yourself essentially acting out what you believe in your daily life, and the question is, where's the proper place to celebrate those beliefs? What you had something at the back.
Oh, yeah, just kind of an interesting parallel with another class on the topic.
Remind me your name, by the way.
Will,
that's right.
I'm also doing a minor in criminal justice, and I just watched a documentary about a guy named Arnie Glasdell.
Okay.
And he killed someone, and in his trial used devil possession as his defense. And so it was kind of a whole documentary about that, way too many visual effects. But essentially what ended up coming up as I was writing is the First Amendment does allow religious freedom and expression in this country, but it explicitly says that religion has nothing to do and is completely left out of any legal proceeding. So it's very, sorry, even though you swear with your hand on a Bible, but yeah, it does say that. I thought that was interesting.
So that is sort of an interesting, unique point about our own country is that for whatever reason, when they built this country, they decided they didn't want religion to be the, let's say, to have authority within the state necessarily, right? And there's been some, and so you mentioned that you can't really use that as a defense. Like you can't claim that, you did it because God told you to and that works, or the devil, or whoever it is, right, as it was in this case. There's been some interesting debates about that. They still have this, so religion still makes its, well, not religion, but, let's say religious ideology makes its way still into the government quite a bit. They have this national prayer breakfast every year, right, the president goes to. And there's a whole interesting secret society behind that too. There's a great documentary about this. I wish I could remember it right now. But I guess they get around it to the extent that they don't claim any particular religion, right? They're celebrating this idea of God, although they don't really define what that is, but they sort of stay away from the religious side of it, which is the structured, this is what God means kind of thing. So they keep it sufficiently nebulous that it doesn't veer into that. But every once in a while, people are getting, raising red flags about this, and it opens a whole can of worms. But and of course, religions are some of the biggest businesses in the country too, right? It's a really good deal to, if you can rebrand your business as a religion, you can basically get away with not paying taxes, which is huge, actually. For normal people like us, we don't think taxes are that big of a deal, but if you're making millions and millions of dollars a year, you're giving away at least half that to the government. And so if you can somehow organize yourself as a religion, then it's a good deal. So religion occupies this strange role, and I think that gives a lot of cynicism to the idea of religion, yeah.
Yeah, I find it, because I was raised in religion like that, and when I look at it now, it's so misplaced in the court system for like all the different cultures that make up our country to come in and swear obedience to this one streamlined religion and then sit down and feel like you're going to have an honest panel. Like I always said, if I ever got caught doing something, I would stand up and claim Satanism and say I can't get a fair trial in this court because your religion directly conflicts with mine.
That would be a hell of a battle to make that defense. I would just stay away from the court system as much as possible. It's true. It is an interesting artifact. I mean, but I think that's the thing is like, look, it works. Like, if people did actually, we don't, but if we all had the same religion, then then swearing on a Bible would make a lot of sense, right? It would be like, okay, we all agree that, this is our value structure. We're going to swear on our value structure, and therefore, somehow we're all on the same page. But yeah, that's less and less of a thing. Now, you made the point about, I made the point, and you echoed it about science as being an interesting value structure too. What do you got? I know I'm going kind of along with this, but I think this is a really important discussion, and I want to get your thoughts. Do you guys think that science is capable of pointing us towards a value structure, a shared value structure? Is it something that science can accomplish? Yes. Tell me your name too, by the way. Okay.
I think, yes, it's possible. Like, for example, the way that people will say, for example, we need religion because that gives us a reason to get married. Why would you get married if you don't have religion and God and all these systems that say you need to do these things? But if, for example, science can prove that a child needs two parents, right, for a child to grow up healthy and to function properly in society. So we can base our morals on science. By just seeing how, because we know children actually make up the next generation. So if we just look at how children will be raised and what makes them healthy, for example, this is just one. You can make morals based on that and decide what's most important. And
I think that's why it's so persuasive. So just to summarize what you're saying is that ideally, particularly with science, in the best case scenario, if we're most generous, we're able to look at some phenomena, even an aspect of society, like how people, the outcomes of their life satisfaction or their success or the success of their children, that we could ideally objectively look at that and say that behaving in a certain way leads to a certain outcome, and that's essentially a matter of trial and error. We've tested it out. We've run the stats, and this is the answer, and that's how we should behave. Okay, I want to respond to that too, because I have some skepticism about it too. But I think that is essentially why people believe that science could lead us to a value structure. Does anybody?
I don't know if I believe it.
Yeah.
But it's like
Right. That's the logic. That's the sort of logos behind the idea.
I think it could, the simple fact that you just need fear to have religion. You have to have fear of something for consequence. And I think science can definitely substitute that.
Oh, that's really interesting. Yeah, science. You mean like by organizing like meta-narratives, right? Like our planet's gonna die or something, right? The oceans are gonna boil off, these kind of things, right? Sort of puts the fear of God in you. That's really interesting. Does anybody have? Yes.
how should that experience changing?
That's the trickiest part, and that's what I was going to bring up. Let me come back to that. Remind me your name again? Emma. Does anybody else have any thoughts about this? Yes.
I think, as you've said before, there are so many sort of structural and institutional parallels between religion as it has been used in like a societal cultural context in the past and science now, that if you're going to use science as a belief structure, you have to be really careful about falling into the same traps that people have fallen into with religion in the past, becoming overly dogmatic about your beliefs, and then, you know, using that to potentially oppress people. I mean, eugenics and social Darwinism were both sort of pseudoscience.
That's a great point. Oh, those weren't even pseudoscience originally, by the way.
Well, that's what we would consider them now, but yeah, they were hard fact.
They were hard fact.
According to the people who were developing them at the time.
Right. I think I'm glad you're aware of that. So he brings up the fact that we can, just like religion, we can fall in love with our ideas, and they can become these sort of gargoyles, these like concrete facades of something. And you bring up the point, like how do we change our minds as we go ahead? And and also you bring up the point of all of the terrible science that has actually been hardcore institutional, like the eugenics society. Actually, the basic lineage of the eugenics science that was later adopted by Hitler in the Second World War was all started in the United States, and it was very much institutionally ratified, right? It was very much institutionally supported science that, there's some people, they're just kind of born, whatever, not up to snuff, and we should probably make sure they don't reproduce because that will lead to a better outcome. Now, that was perfectly rational to those people, is what right? They made these analyses in some sense. They looked at the data, they did all the statistics, and they were like, yeah, it's probably going to be better if these people don't breed, right? Now, what's the problem with that, obviously? Like, what do you miss out on? Well, maybe, think about all of the incredible acts of genius that have come out of people that are like completely dysfunctional in many ways too, right? There's a great deal of diversity of expression and contribution to humanity, right? Not everybody has to be like a super athlete with a 1600 on their SAT to do incredible contributions to humanity, right? So this is kind of what I'm getting at is whenever you have a very tunnel vision view of how you're going to measure something, what its outcome should be, you absolutely run the risk of missing all of the second, third, fourth order effects that result from that. And the things that you're not studying are the things that you often miss out on. So, yeah, of course.
I just think that, for example, if we base how we function in society on science, the way that we did for many, many years in America and Christianity, for example, then it would still kind of be the same thing where we'd have a general direction of where we want to go for most people, but we're still going to have outliers. Not everyone practices Christianity in the same way. They'll have their own interpretations, and I think science would just replace that.
Yeah, I mean, I hope that you're right about that. And I think that's very possible.
And I'm not like it, so that I'm like, that's not the science.
Right. Well, yeah, fair enough. So that brings up an interesting point too. And I mean, I don't want to interrogate you in public about your particular experience. I think that's not totally fair, although I'd love to. But the fact of the matter is also there's a completely different idea, which is like science is really good at establishing a certain kind of truth, right, with respect to material mechanics and systems dynamics and so forth. But that, let's say, religion or let me generalize it into spirituality in general, accesses a very different kind of truth, which is something like how to behave yourself in order to, let's say, make yourself happy, right? So there's honestly like a very good case to be made that there's two kinds of intelligences. One is an intelligence that's capable of addressing established problems, right? So there's a super genius type of person who, if I give them a problem to solve, and it has an answer, that they can get to the bottom of that answer. There's a personality type that's really suited to that kind of intelligence. But there's also a personality type of somebody who is capable of identifying new problems in their own life, for instance, or anywhere, and seeing things that weren't really problems to begin with, and solving those kind of problems. And the religious way, the spiritual way of looking at what is true in any situation might be more apt to that other kind of problem solving, where it's like, how do I have a good day today, right? I don't know that, science might be able to point you to some studies of what other people have done to make themselves happy, but it might be different than your own experience. And so maybe there's a different teaching set. Maybe there's a different way of looking at it. That's the argument anyways. Because the funny thing is, there's actually a lot of scientists who are also very religious, which is surprising. You would think that if science was actually a good replacement for religion, that would never ever happen, because the best scientists would be like, oh, well, I've got everything I need here. But it doesn't seem to be the case, and that's really interesting too. Okay, any closing thoughts on this? We've gotten pretty far down the rabbit hole, but it's such an interesting topic, and I would love to hear everybody more thoughts too after class or before class. We'll do another coffee hour on Thursday. I'd like to hear more thoughts on this because it's interesting to hear how young people are taking this. It's already changed a lot since I was in college. There's less. Seems like there's less people practicing religious faiths nowadays than even 20 years ago. Okay, so I want to make sure that we get caught up a little bit, and I need to get through the planets and start to get into the real nitty-gritties of star formation and star adolescence, let's say, and work towards star death, which is where we're headed. By the way, it's so funny that we use these words birth and death, right, with these stars. Like, we have no other way to handle them and make sense of them. If anybody can think of a better word than that, I would appreciate it. But obviously, scientists don't believe that stars are alive, and so it's kind of funny that we treat them this way. But we do. So I introduced this idea that the Greeks, of course, had these personality types, these mythologies. They actually named the planets after them. They thought of the planets in some senses representing the different emotions, right? Obviously, we don't think of them quite that way today. We think of planets as these non-luminous bodies that orbit stars. And that's, of course, been thrown into some chaos lately because there's obviously planets now that aren't orbiting stars. So what the heck is a planet? Do we have to put planets on the same, HR diagram as stars eventually, right? Do all these astrophysical bodies belong in the same context? I don't know. That might be an outcome of this. But what we do know is that for the first time in all of this theorizing about where planets came from, we've actually been able to see some exoplanetary systems. And so that has radically changed things in the last, I would say, mainly 5 years, but the first exoplanet, I think, was discovered in the 90s, but, n equals 1. Having one example doesn't allow you to make a lot of statements. Although, as the data kept accumulating, and I'm going to show you some of this data on exoplanets, we started to realize that our own solar system was pretty unique. It wasn't the way that most solar systems looked. And that really, really has stirred things up because for 300 years we've had this story about how our solar system formed. And it was based entirely, we had this story of how solar systems form, and it was based entirely on our own solar system. And so now for the first time we're able to look at things a bit differently. So, here's a few examples you see here, up here. Let me see where these are from. So these are taken by the Hubble Space Telescope. This is in that Orion Nebula. So we keep coming back to the Orion Nebula. It's one of the most visible clusters in the sky. And it's where we think a lot of stars, new stars are being born, planets are being born. So the size of each one of those images is something like 30 times the diameter of our own planetary system. So they're much bigger than the actual planetary systems that they end up creating. So the mass in these disks is something like less than 10% the mass of our own sun, but it's much more than the mass of all of our planets put together. So there's a great deal of material in each one of these disks, and these disks are where we think things are starting to heat up and where things are starting to result in planet formation. Now, the story that I'm about to tell you for planet formation, it doesn't take into account these things like planets without stars, right? So, and I'll keep trying to interject this as we go along, but this narrative that we've inherited that's in this textbook that I'm kind of walking you through right now, it doesn't actually account for the fact that there might be some other roads to planet formation that we're not considering. For instance, where in the world do those lone pairs, those sunless planet systems come from, right? And we've touched on this before. What's the difference between a brown dwarf and a sun? Well, it's just a few atoms at some point, right? So they're smaller. They don't have enough atoms in one place to actually ignite the fusion necessary to make a star. So maybe some of these things that look a lot like Jupiter's are actually failed stars. Maybe they're stars that lost some material, that they got ripped off by another star and they shrunk back and stopped glowing. That's one I haven't really seen seriously entertained in the literature, but I think it's completely reasonable. So maybe there's this other pathway too, in addition to the one that we're going to keep exploring here, to get planets into creation that involves something closer to the formation of a sun, but not quite. Maybe something goes awry, and they ending up inside of a solar system, maybe, as a star passes nearby with the appropriate momentum, or they get kicked out and they join a new system. Okay, but the story that we're talking now is assuming that the planets form in situ, which is this very old, 300-year-old idea. The planets form essentially where they are, there's been, they adapted this idea in the 1960s, back half of the 20th century, to the idea that planets, especially the Jupiters and Neptunes, might migrate around a little bit over the early development of our solar system. But essentially, the planets form with their stars. And I'm focusing on the problems with that idea because I think they're more interesting than the 300-year-old idea that they form in place. So my sense is that there's probably a number of different ways to bake a cake. And it's going to be proved very difficult to separate out which one happened. But let's work towards that. So what we do essentially is we look at how these disks change over time, and we estimate how long it takes for the planets to form from it. This is the standard method. Now, so if you measure the temperature and luminosity of a protostar, this is what we were talking about at the end of class last time, then we can put it on the HR diagram, so on that star evolution diagram. And then we compare the real star with the models of how the protostar should evolve with time, and we estimate their age. And so what's interesting is that if you see a protostar that's about 1 to 3 million years old, its disk goes all the way from the surface of the star out to hundreds, maybe even thousands of AU away. And in the older protostars, you find the disks still have a lot of dust and so forth, but the inner regions are almost entirely cleared out. So there's like a gap between the star and so forth. So there's this idea that the disk itself is evolving. And what we've started to think is that as the planets, well, this is not what we've started to think. What people have thought, since they noticed this and they want to fit this into this older conception of this in situ formation, is that those gaps are actually being hollowed out because the material is being accreted into planets as it's going along, which is like completely reasonable, I suppose. Now, the calculations to make this accretion process happen, right, this essentially gravitational collapse of dust and gas in the disk, it works really well, and I think we mentioned this before, it works really well up to a point. So for really small, like dust grain-sized particles, you get low density interaction. And people have substantiated this in recent years with electrostatic interaction, so chemistry essentially. Or if you want to think about it like static charge, right? So dust might stick together. You mentioned last class these dust explosions, right? And I think in some sense that's the result of the buildup of static charge in igniting other combustion reactions. But there's a lot of static charge in the dust. So you get these small grains that clump together. However, the planetesimal formations, that's the baby planet, in the centimeter to meter range is really poorly understood. This seems to be, we're at a point where there really hasn't been any convincing explanation as to why grains would accumulate rather than simply bounce off each other. So things on the order of the size of a pebble, right? What in the world would make pebbles stick together? Nobody's actually solved that problem, which is the most disturbing part of the story that I'm telling you today. Because we're jumping very quickly from this point where we have this nice grain of, this nice dust, these nice dusty disks. Some of them seem to be evolving. There's hollowed out areas. The interior's hollowed out. So far so good. But then how do you stick the little pebbles together to make a planet? Nobody's solved that problem. Your textbook says this. It says, once the clumps grow to about 10 centimeters in size, they enter a perilous stage in development. At that size, they can grow to larger than 100 meters in diameter, but they're subject to drag forces produced by friction with gas in the disk, and their orbits can rapidly decay, plunging them into the host star. What's interesting is they sort of jump over the point that it gets to 10 centimeters in size, which seems to be really tricky to do in the first point. But then they say it has to grow really big, because if it doesn't, it's going to basically get kicked out of the dust ring and get swallowed by the star. Now, all of this also raises this really interesting point too, which is that the Earth that we're standing on is the most dense body in the solar system, which is very bizarre because you would think the most dense body in the solar system, according to these accretion dynamics, would be in the center of the solar system, And of course, there is very dense point in the center of the sun, but the sun on average has a density, closer to water, honestly, than to the Earth, which is something like 5 times that. So what's going on there? How in the world do you end up with these really dense rocky bodies outside of it? And I don't know, I never get a satisfying explanation to that when I'm talking with my friends who are doing these kind of modeling projects. And we'll get around to some alternative explanations for that eventually. So the basic idea then is the idea that these people are proposing is that they do somehow cross that meter-sized barrier. They become boulders, they stick together. Basically, gravitational accretion takes over, squeezes them down. If they grow fast enough into something big enough before all of that gas can disperse, because remember, this baby sun is putting out a lot of solar wind, right? And so it's kicking off all of this dust and gas as it evolves. And this has to do with why it's clearing out that ring right around itself as well. If they grow fast enough, then they can actually start to grab a hold of some of that gas. And the idea is you can build a gas giant in this way. So what's really interesting is this entire process requires a very short timeline. So you need to build these planets in a matter of a few million years, essentially, right? Because you're not going to have the gas and the dust hanging around long enough otherwise if you don't do it that fast. Now, I've always been a little bit troubled by that because if you think about it, our planet that we're sitting on right now, we've had life on this planet. It's fairly convincing arguments that life's been around for something like 3 billion years. Now, billion years is 1,000 million years. And so the argument that the planet is constructed in 1 million years or 2 million years or 3 million years, it really strains the imagination. That's extraordinarily fast on geological timescales. So this is tricky. And we'll play with some alternative mechanisms in a minute. Now, what's contributed to moving us closer to something that makes a little more sense, like I said, has been the discovery of these exoplanetary systems. This is actually the first one that was discovered. This was in 1995. And we'll reference this one a few more times. Now, the nice thing about this exoplanetary system is that you're seeing it from the top down, right? When we think about, whenever you see a map of the solar system, you always see it from the top down, right? From the North Pole side down, which is that's a whole other discussion, why in the world we look at it from that side and not the other side. We'd have to get into some serious colonial politics to make sense of that. But needless to say, it's easy to see because we don't have, when planets are on their side, when the solar system's on its side, some of them are obscured by each other, some of them are hidden by the sun at any given point. And so, of course, the first discoveries were top-down discoveries. Now, the idea that there would be other solar systems has been around for a long time. We talked about Giordano Bruno getting a lot of, this famed story where he's burned at the stake for saying there should be other worlds out there. It's obviously a bit more complicated. I think he actually got burned at the stake for essentially arguing with the church about theology. Again, Isaac Newton comes along maybe a century later and also echoes this idea and says, well, if there's stars, if these things are actually stars just like our sun, then they probably have systems organized very much like ours. And that's as far as he goes with it. He doesn't push it much further than that. And these were kind of a theoretical curiosity really up until the 1990s. That's what's absolutely shocking about this. It's like everybody seems to have realized there probably are other planetary systems, but we don't know for sure. And so it was in some sense this inevitability, like kind of the way that people talk about life on other planets right now, right? Everybody's kind of like, well, there probably is, right? But we've never seen it before, and so it hasn't really entered into our theoretical landscape. It's still a hypothesis. It's still this sort of unproven statement. Now, most exoplanetary discoveries are not made like this. You can't just actually take a nice picture of them from the top. Most of the time we have to look for a couple of things. One of the easy ways to do that is to see the planet periodically cross in front of the star. So it dims the star's light, right? Now that only works for for a planet that's really big and really close to the star. If it's big and far away, you won't see it. If it's small and close up, you won't see it. So you're screening for a particular kind of exoplanet. The other thing that you can do is you can look for a little gravitational tug on the planet. on the star. So like I said, Jupiter is so big that the sun and Jupiter actually orbit a point that's like a tiny bit outside of the sun, right? So there's a little bit of a wobble. If you looked at the sun, our sun, from outside, from another solar system, you would see our sun making this little tiny, almost a little tiny orbit, really, like this, because it's getting yanked around by Jupiter. Yes?
There's a lot of theories about how Jupiter is technically a failed star. Would that mean that in our technical solar system, since a lot of them technically usually have two suns orbiting it, do you think Jupiter was possibly supposed to be the second?
I mean, when you say there's a lot of arguments about that, are you saying that I've made a lot of arguments about that?
Just in general.
Or you've seen these elsewhere. That's interesting. Yeah, every year that goes by, I see that being a more closely entertained idea. You know, that was completely out of the question when I was in college. Even last year, it seemed like less of an entertainable idea. I think this discovery of these planets orbiting each other with no sun has really opened people's eyes up to it. Remind me sorry, what was the question?
Do you think that possibly Jupiter was supposed to be?
Oh yeah, a binary partner. Yeah, so most, let's say 80% or more of the stars that we can see have partner stars. Why doesn't our star have a partner star, right? It's very bizarre that it wouldn't have a partner star, at least just statistically speaking. So there's a couple of options there. One is that it used to have one. One is that it's just one of those fluke stars that doesn't have a partner star. Another is that we do have a partner star, but we can't see it. And somebody's made that presentation to me recently on my podcast, actually. This guy named Walter Cruttenden. He's not an astronomer. He's just this like wealthy financier who retired from finance industry and spent his life researching this. And he's convinced that there is one star that's actually approaching us very rapidly. It's called Barnard's star. You can read about it on Wikipedia. He's convinced that Barnard's star is our partner star, and he has this whole argument, which is actually pretty well built out, but I don't think anybody agrees with that in the mainstream, at least at this point. I'll be interested to put it in front of other people. And so the other possibility is that maybe if our star had one, did that star die violently? Which would be interesting because maybe that would explain some of the strange anomalies in early Earth, right? There's 1 billion years of rock scoured off the face of the Earth. You can go see it in the Grand Canyon, just completely missing, right? What the heck happened then? That was, I believe it was, I don't want to get this wrong, but it was a long time ago, right after life appeared, actually. Another possibility, and this is one that I've never heard anybody make this argument. Well, not nobody, but I've never heard anybody in the academy make this argument that the difference between, I keep making it to you guys over and over again, I'm just doing it one more time. The difference between a sun and a brown dwarf is one atom at some point, right? So it seems perfectly logical that a star, for whatever reason, could lose that mass and stop glowing as a result of it, not have a violent supernova death and so forth. By the way, we see very, very few supernovas, right? And we'll talk about the different ways stars die later. We'll get more into that. But one possibility is that, yeah, the star actually becomes something that looks a bit more like a brown dwarf. A Jupiter is essentially a planet that's a little bit smaller than a brown dwarf, but compositionally speaking, they're almost identical. They look the same. They're even the same radius. It's just that there's more stuff crammed into a brown dwarf than into a Jupiter. So you asked the question, could Jupiter be a leftover partner star from our sun? I don't know. I mean, it seems possible to me, but the timescales that we have for a lot of these processes would preclude that, I suppose, because, well, I don't know. In some sense, I think it might be one of those moments where we're so inundated with data from these star systems that the theoreticians are having a really hard time keeping up the textbook with all the new discoveries that are happening, essentially, right? How do we put all of these discoveries into their proper place in the theory set that we've developed over 300 years since, let's say, the birth of modern science, right? Which was kind of this Baconian, Galilean idea that we do experiments, we test hypotheses. That's been around for like 300 years. And we've had this model of how the solar system forms, which is basically the one that's in your textbook, for about that long. But there's all these weird pieces of data that just don't fit into it. And I think it's proving very difficult to keep a homogeneous narrative going. Or they might, like I keep saying, for me at this point, at looking at all this evidence, I see there being potentially a number of different ways to form planets. And your textbook deals with one, but there might be other things making its way into the textbook next year. We'll see. It's cool. It's an online textbook, so it does have the ability to update as things go on. So, yeah, Jupiter's a weird one. I mean, compositionally speaking, Jupiter's is very similar composition to the Sun itself. They're both made out of the same stuff. One's just smaller and colder than the other one. All right. So this is the basic idea I was talking about. You can see the wobble in the stars. We use that radial velocity method to actually get a sense of the motion of a distant star. We talked about this at the beginning of the course, so I won't bore you with it all over again. One of the first ones that we ever saw using this method was we found a planet orbiting a star that was about the same size as our sun, and it was in this constellation Pegasi. I think that's kind of interesting too. Again, all of these constellations, all these stars, we keep naming them after these Greek myths, right? So Pegasus is, of course, the horse that our hero rode in on to save the princess, who was it, Andromeda, in the myth that we were talking about. And Pegasus is an interesting character which sort of, represents this sense of inspiration that appears, which is this fleeting, ability to transition between the different subroutines in your own psyche. So you see that crop up again, which is just fascinating. I just think it's really interesting how we can't let go of these myths. They're too important to us. And these are scientists, by the way, just to talk about these, go back to what we were talking about at the beginning of class. The scientists themselves are the ones who are naming these objects, and they're the ones bringing the myth back in, which is fascinating. For me, it points to the fact that there's almost two ways of approaching understanding the universe, and they're somehow mutually exclusive from one another. They address different aspects of reality. All right, so this planet, I don't know how much details we need to go of. It was pretty big, so not a terrestrial type of planet. It's very difficult with this method, the wobble method, to see anything that's small like the size of Earth, particularly the size of Mercury, something like that. This was a Jovian type of planet. And so there's this idea that these methods are introducing a really strong selection bias, right? The other method, of course, where you see a planet transiting past the sun is going to leave you with a similar selection bias. You're really only seeing the big, massive stars, wide radius, stars, I said stars, I mean planets, in these kind of contexts. So you're only really capable of selecting for planets that will show up on your detector. Now, there's been other ways of estimating by the effects of those planets being tugged around, or more recently by looking at the atmosphere of smaller planets, right? So it's Neptune-sized, sub-Neptune-sized, slightly larger than Earth-sized planets. We're starting to be able to see those things by noting the way that the sunlight refracts through their atmosphere. And so we can get some estimate of there being these sub-Jovian type planets as well as a result of these new methods. And there's been a couple of different missions to do this. I think I might have pointed this out to you earlier. Initially, there was this Kepler Space Telescope. I believe this was launched in the early 2000s. And the update to that is called TESS. Now, TESS is looking in every direction, whereas Kepler looked only in one direction. And I believe that TESS has cataloged something like, several thousand of these exoplanets at this point in our local neighborhood. And the results are actually quite interesting. So this is where we get into the meat of the discussion. Because what we find, actually, so what we're looking at here in this diagram is we're looking at I think the most important thing here right now is the size relative to Earth. So a 1 over here is the same size as Earth. So we can think about Earth has orbital period is days, right? So how fast it's going around the star. So Earth would be way down here in the bottom right almost, right? A 1 with about 365 days, right? Now, what's weird is you don't see any Earths here, right? I guess that sort of makes sense because Earth would be a very difficult planet to detect. But what we do see is a ton of these planets that are bigger than Earth, but smaller than Neptune. Now, why that's interesting is because we got 0 of those here in our own solar system. We have Earth, and then we have Neptune, and nothing in between, which is very bizarre because that seems to be like the most common type of planet in the solar system. Here's another way of looking at it by planet size, so Earth being 1, and the fraction of planets observed. And you see the most common type of planet is in this gap at the top where we have none of those planets, right? Now, that brings some really interesting debate to the room, and these debates are absolutely ongoing, and nobody really knows why this is. So again, we start thinking about this question of, we have an anomaly in our solar system, like you were mentioning earlier with where's our partner star? That's weird, we don't have one. Well, what are the options? We lost one, or it evolved, right? I'm retooling this course more and more for next year in particular I'm even changing the title of it, to be about the evolution of these bodies, right? Because I think we need to start thinking about them in a Darwinian sense in some fashion, at least some parallel that's closely analogous. You know, most of the ideas about why our solar system doesn't have these come down to the fact that they crashed into each other and exploded and so forth during the early migration phase, which, you know, that's a reasonable argument. But I think there's another reasonable argument too, which is that something that looks like Neptune, if it finds itself a little too close to the sun at any given point, what's going to happen to all of that volatile ice and water and stuff? It's going to get cooked off, right? And what happens to a Neptune if you cook off its atmosphere? It looks like Earth, right? So the hypothesis that I'm putting out here is that could the Earth actually have spent some time looking like a Neptune in its early days? Now, it's a pretty radical hypothesis, but there's been some interesting literature to substantiate this. There was a group that published a paper in Nature, I think in 2022, where they considered a very similar hypothesis concerning the evolution of the Earth's oceans as the result of the condensation reactions between oxygen, a huge, thick atmosphere of oxygen and hydrogen. So the thing was closer to Saturn's composition with a bit of Neptune-like composition as well before it evolved into the ocean world, which is typically where our timeline for events on Earth start when you talk to geologists and things like that. So it's not completely nuts, you know, and there's some other really interesting evidence about that too. I think I may have mentioned it before, but particularly the dinosaurs. There's a couple of weird things about the dinosaurs. First of all, you take something like a Brontosaurus or something, or even a T-Rex. Now you can do very basic material science calculations to examine the stress and strain of an animal of that size on its bones, right? And it's very perplexing to scientists because you can't actually stand a dinosaur up and walk it around. Its legs would break under its own weight. It doesn't really work. And so the argument is given, okay, they actually spent most of their time in the water. So they were in these kind of boggy, murky, marshy areas, like the Brontosaurus. You know, that makes a lot of sense. Actually, the Brontosaurus has, not the Brontosaurus, but some of those big, the Brachiosaurus, they have these blowholes on the top of their head, kind of like whales or something. So you can kind of see it for those animals. Okay, fair enough. However, there's these strange, they're technically not dinosaurs, but they were alive at the same time. They're called Quetzalcoatl, and they're essentially these pterodons. So they're huge birds, like the size of a 747, right? Now, what's really bizarre about these bird-like animals is that you can do a very quick calculation of wing size to mass ratio in order to determine if an airplane's going to fly or not, right? Or it's going to glide at least, right? These animals don't meet that criteria. They're completely outside of the flight diagram for wing loading versus mass. So they're too big to have flown or even glided, but they have huge wings. So the question becomes, what the heck's going on? Now, I met with this, actually a guy who ended up, he was from Oregon. He did his PhD at University of Oregon under Octavio Levenspiel. And together, the two of them proposed this idea that actually, in the time of the dinosaurs, the atmosphere, if it was only 3 times as thick as it is today, then these Quetzalcoatli would actually be able to fly, right? Because you would have buoyancy added by the support. Just like when you're in water, it's very dense, and so it lifts you a little bit. Or let's say it works against gravity. And so their proposal was that, hey, actually the atmosphere may have had the same partial pressures, right? You'd still have whatever it is, 20% oxygen, 80% nitrogen atmosphere, but the relative amounts of it would have been packed in tighter and it would have been denser. And if it were the case, there'd be no geologic record of that. You can only tell composition, you can't actually tell pressure. And so this is perhaps the only way we can explain these dinosaurs. The alternative is that they just evolved wings for no freaking reason whatsoever, and they have wings, but they didn't fly. It's very bizarre. What's that? For mating? Yeah, maybe it was like the penguin, or like the, what am I thinking of? Peacocks. Yeah, peacocks, ostriches. All right, fair enough. Absolutely fair. But, you know, should we expect that a planet could exist in a solar system for at least 4 billion years without changing its phenotype, for lack of a better word? I don't know what the astrophysical equivalent of phenotype would be. Its appearance, its shape, its morphology. I mean, I would expect that I would expect that there should be some changes across time. Now, this is substantiated further, this line of thinking, by the fact that we see now in some of these exoplanetary systems, what we can see is these big Neptune-like planets that have gotten too close to the sun. And their atmospheres are being cooked off appreciably, right? So this is a thing that definitely happens. The question is, could it happen fast enough given the time limits that we've put on our solar system? Now remember, we've put this time limit on our solar system of 4.5 billion years. Where does that come from exactly, right? Well, in some part, it comes from the dating of the rocks in our solar system, which I don't remember. I can never keep track of what I've talked about in this class versus last semester. But I believe I've explained it to you in so much as that our dating techniques really just tell us the last time that some rock was molten. And so we don't really have a date for the beginning of this thing. So we don't really know how long it's taken. So there's more questions than answers here, I guess, which I find really exciting. and I hope that you do too. But needless to say, the ability to actually see all of these new solar systems with their strange layouts that's very different than ours has opened a number of doors in the theoretical landscape. Another thing that's quite interesting, most of the exoplanetary systems we see are of this grouping down here called similar. They call them similar kind of arbitrarily, but let's say all of the planets are the same size and mass for the most part. You know, that kind of composition. Oh, by the way, they'd all be basically super Earths or mini Neptunes, however you want to call it at that point, because that's the most common type of planet, right? And they're all similar. Now, that kind of an organization makes a lot of sense in the context of this accretion model that the textbook is presenting to you, right? Where everybody's kind of doing the same thing, they all look about the same and so forth. That's interesting. Now, a minority of them have mixed up, right? The size of the planet has no correlation whatsoever to where it's located. Some of them, very few, are anti-ordered, so the little planets are farthest away. And then there's a few that are ordered as well. So let's look at the actual data here. Most of these are models. The orange dash is actually from observations, and it looks like most planets are binned into being similar, with the right behind them being the ordered ones. They call our solar system ordered, but it's unclear to me if that's a totally reasonable assessment. Of course, depends where you put Pluto, right? I guess we've decided that Pluto and some of the trans-Neptune planetoids are not sufficiently big to be called planets. But if they were, it wouldn't be ordered in the same way. So most of the planets are similar in these systems, which is really, really, really interesting. Ours appears to be a bit different. So it seems like some changes have taken place. Again, some sort of evolution of this system has occurred across time. Now, people have been examining the ways in which that's happened, particularly with respect to Jupiter and Neptune's formation. Those have been considered. I think we mentioned, I can't remember anymore. I believe we've talked about Jupiter migration in this course, if not last semester. And honestly, we don't really have time for the details of it. since we need to be getting back to the stars as soon as possible. Now, there's different mechanisms made for how in the world Jupiter would make its way in and out of the solar system. A lot of it has to do with it interacting very early on with that dust disk, right, before it's blown away by the solar wind and it can actually move and find its way to its present location. We'll see what happens with that debate. I think that it may also be, like we said earlier, illuminated by the discovery of these free-floating Jupiters as well. Maybe they're forming somewhere that has nothing to do with the solar system itself. Or at least maybe they're part of a binary partner at some point. You know, it's also possible we didn't even address this issue that maybe all of the binary, trinary, quaternary star systems, they all start off as groups of Jupiters that continue to accrete material onto them over time and grab stuff up over, you know, gazillions of years. And some of them start to fuse at some point and become stars. And some of them aren't, and they become the first planets in that star system. That's a reasonable hypothesis, too. All right. I'm going to try to start into this week's material as soon as possible here. Okay, let's skip over, let's get outside of, let's stop thinking about planets for a minute, because honestly, if you really want to learn about planets, you need to take the first semester of this course, where we have the luxury of time to unpack everything about them and their formation processes. We need to get back to talking about stars. So, and to get back to the point, I forget who, somebody raised at the beginning of class, it is fascinating that we do need to have stars in order to make stars, which for me, really, as far as cosmological models are concerned, it really points to an interesting kind of cyclic cosmology, which has been championed by a lot of cosmology being a very modern science, but cosmology as a practice being the understanding of the universe is something that all cultures have developed for thousands and thousands of years. And many cultures develop these cyclic cosmology where, you know, things come and go, but they essentially perpetuate in this cycle of coming and going eternally. Now, stars, in some sense, seem to echo this. Of course, we have imposed this more linear perspective on them because we obviously, but our modern astrophysical community has a firm belief in a birthday for the universe, which gives it a sort of linear production to the story that we'll tell cosmologically about this place. Now, the story is that there's been generations of stars. The first generations of stars just made the light elements. Some of them accreted a lot of material, and in their supernova, as they were dying, they gave off some of the heavier elements. And we scooped up, you know, the leftovers. So we're in a second or third generation star. So what is it like to age as a star? That's the question that we're going to be exploring for the rest of the week. You know, up to this point, we've imagined how you become. It's very difficult not to anthropomorphize these bodies into living beings. But how, as a star, how do you start to accrete material, you become stable, you're undergoing this very basic fusion, this hydrogen fusion we've talked about, squishing together some hydrogens. That's all very easy to understand. But what goes wrong at some point? You know, the idea, of course, is that stars don't live forever, that they age. As they age, changes take place. And as they do, we can see those changes and infer what's happening. Now, a lot of this comes down to examining the HR diagram. So this diagram that I keep bringing up over and over again, right? This is, we could say, what is apparent when we look out at the sky. We can see all the stars clustered into this arrangement of various luminosities and temperatures. Now, this diagram is ideally based on direct observations, but as we know, luminosity is not something that you can directly observe. You only get apparent brightness, and so you kind of squish it around. So this isn't entirely a direct evidence thing. But what we do is we work with it. We accept this as our basic model for the layout, and we try to explain the different stars that aren't on that main sequence, right? And that's where we get into the more interesting pieces of this story over the next couple of weeks, because one of the difficult clusters here to explain are these red giants, right? So they're very luminous and they're cooler than stars on the main sequence, right? They're redder as opposed to being bluer, like a flame. So how do we explain those? Now we've played with this idea that some of these other outliers, let me go back to this other diagram, that a few of these outliers, up towards the top left, you see there's a few dots hanging around there. There's a few dots down, off to the right-hand side of the of the main sequence on this diagram. We played with the idea that we could explain those as protostars that are starting to collapse, right? And they're becoming, in some sense, at first, as they collapse, they're losing brightness, but then once they actually start fusing for the first time, then their luminosity increases, right? And they actually work their way there. They get more temperature, they get hotter, and they work their way onto the main sequence. So that was an example of how you can hopefully tell the story of these outliers in the narrative of how these stars are constructed. Again, it's the best we have, right? These stories that we're telling, we're literally looking at these dots, which you can think of as frames in a movie that are completely shuffled up on the floor. And we're trying to put those frames from the movie in order. And so this is the best way that we have for going about it. Now, so what's happening here? The temperature and density of the inner region of these stars is slowly increasing as helium accumulates in the center of the star. So fusion's going on. It's getting denser, right, which is cranking up the pressure of gravity. It's also leading to contraction, which is raising the temperature. And the rate of fusion is, of course, going to go up as the temperature goes up. So all of this pressure, this goes up, I think the rate of fusion goes up by about the fourth power with respect to temperature as it goes up. So as the fusion goes up, the rate of energy being generated also increases, and the luminosity of the star also rises. And you get a sense of how long a star can stay on that main sequence, and these are just some values for how we give its age. How long it stays in that main sequence of burning hydrogen for fuel down to helium really has a lot to do with how big it is, right? So how much nuclear fuel it has and how quickly it uses up that fuel. So because massive stars have a lot of fuel, but they also burn it really, really fast, and so their lifetimes are much shorter. And so this allows us to estimate the age of these stars based on their luminosity and temperature. Right? So now we're 3 orders of abstraction away from the actual direct evidence. But it is a reasonable story. I don't have any problems with it. I don't know that it's true or not, but it is a well-reasoned story. Now, we developed our sun is a G-type star, right? It's kind of run-of-the-mill. So we probably shouldn't waste a lot of time when we talk about exploring the cosmos, investigating stars that are much bigger than our star, because they won't live that long, right? So if we're looking for life out there or potential habitable zones for our own species in the future in other star systems, it doesn't make a lot of sense to look at like O-type or B-type stars because they're only going to be there for a short while. That's the way people are thinking. Now, what if planets can trade between systems, however, right? That's a reasonable possibility as well. Could one planet start off in one system and end up in another? Maybe, but the timescales become very difficult. So in the last 5 minutes here, I want to walk you through what it looks like to leave the main sequence. So the first steps, let's say, of, gosh, it's so hard to talk about this without using human terms about life and death. I actually just don't even know how to do it. Let's just say as the star metamorphosizes into a different shape, a different phenotype, there's some interesting changes that take place. So let's just go through these so we can pick up with these red giants next time. So the basic idea, and let me take you back to that HR diagram really quick, is that these stars on the main sequence, this main thick line here, they need to move into this red giant phase. And we use the red giants, we think the red giants used to be on the main sequence as part of this story. So the question is, how do they get there? And the story goes something like this. So eventually, all of the hydrogen in the core, where it's really hot, is used up in a star, just like our sun. So then the core only contains helium, which is, maybe contaminated with whatever big stuff has fallen into the sun over the course of its life. Because, meteors and so forth, maybe entire planets are getting gobbled up by stars all the time. Now, since the central temperature is not quite hot enough to fuse helium, you need much more heat to fuse a big element than you do a small one, like hydrogen. There's no nuclear energy source to supply the heat to the central star region. So this period of stability on the main sequence ends, and gravity takes over, and the core starts to contract, right? Because remember, in a star, gravity is being counteracted by all of this sort of explosive fusion pressure, right? So there's this nice balance, and the star has the same size for most of its life. But if the fusion stops, then the thing starts to contract again. So as the star's core shrinks, the inward falling material pressurizes it, much like the piston in the car, and it generates a lot of heat. So it starts to heat up again. And what happens is that heat starts to warm this layer of hydrogen that's outside of the core in the star that wasn't being fused before, right? And what happens is it ignites this second layer of hydrogen in a shell right around the core. And so you almost get I don't know what you would call this, a second wind out of the star. And so this is, this actually begins to heat up other layers outside. And as the layers outside the shell actually heat up, they expand. And so the star itself starts to swell a little bit. Now, this leads to a sort of feedback resonance, right, where the helium core continues to contract. It produces more heat, which amplifies the fusion in the shell of fresh hydrogen on the outside. And this continues over and over again. And you can actually get to a point where these expanding layers are actually belching off layers of material at the outside. You get such expansion that you actually lose layers as a result of it, because there's rapid cooling. So one thing that happens, you might have noticed this when you take the lid off of some boiling water, is that this steam actually expands and it cools down. This is called adiabatic cooling. So as you expand something like the star itself, it actually cools down. Then you have this layer of contraction and cooling and contraction and cooling. And so the thing's oscillating, it's very unstable. Now, the result of that is that the star begins to actually depart from the main sequence, and it actually moves its way off of the main sequence. It becomes bigger, right? So its luminosity, its surface area increases, but it's cooling, so the temperature goes down, and it moves slightly to the right on the main sequence. Okay, I think that, let's see here. I think this is a good place to stop, because the next thing that we're going to do is we're going to look at the different cluster types and try to evaluate their age and the timeline of these based on where they're located in the galaxy, and try to put together a bigger picture of how old these systems are. But yeah, let's get together. So Thursday morning, if anybody wants to come early, I would look forward to hearing more of your thoughts about our discussion this morning. I appreciate you guys sharing your ideas. I know it's kind of scary to have opinions about things, but it's very interesting to me. So anyways, have a good week, and I'll see you Thursday.